Hello and welcome to another edition of Ontology Talk. I'm Adam Pease, and today I want to talk about some techniques for learning logic. In other videos in my web series, I've talked about why we need logic, how we can apply it in practical problems in computer science and engineering, but today I want to just focus on how do we go about learning how to do this thing, which is often considered somewhat difficult. So one of the techniques that I often use when teaching logic is to teach people how to read logic. Just translating logical expressions into English and reading them aloud to yourself often can be a very powerful tool for debugging, especially for the beginner. Our intuitions about what makes sense in an English sentence is very strong and much stronger than our knowledge as beginners about what is actually correct in a logical expression. So I try to come up with some phrases that you can use as templates to help you generate expressions in English from the logic that you're trying to write. So let's look at some of these. So first thing, for universal quantification. So this is the upside down A in traditional logic, and in the syntax that I use, I spell it out as for all. So we're saying for all x and y, something is true. Okay, that should be pretty straightforward. And it's often combined with rules. So we have rules that have this particular syntax in the system that I use. And it's a prefix notation, so the operator goes first. And we read this, if A, then B. And this is really very similar to what we'd have, at least on appearances, it's very similar to what we'd have in a traditional programming language like C++ or Python or Java. If some condition holds, then the following. The difference here is that in a programming language, you're saying if something is true, then perform a series of steps, do something. Whereas in logic, you're saying if something is true, then something else is true. You're not saying to do something, you're asserting another truth about the world. If one thing is true, then another thing is true. So if we combine this sort of expression with a quantifier, we have something of this sort. So for all x, if we have a relation R between C and x, then we can conclude there's a relation R between D and x. So these are just arbitrary symbols here, but just to show you the general form of this sort of thing. So here's a more concrete example, and hopefully this is maybe a little easier to understand, especially for people that are scared off by equations, including myself. I much prefer concrete examples, real-world examples. They're much easier for me to get my head around. So here's another one that says, so for all x, if x is a racehorse, then x has the attribute of being fast. So for all x, if x is a racehorse, x has the attribute of being fast. Now, in the syntax that I use, variables that are not explicitly quantified with a for all or an exists, and we'll get to what exists is, an existential quantifier, we'll get to that in a moment. If there isn't an explicit quantifier, then we just assume that it's universally quantified. It's implicitly universally quantified. So we can actually get rid of that for all up front, and the meaning is exactly the same, but it's a little easier, simpler, quicker to write. It's fewer keystrokes. Why not? So another way to read this is simply all racehorses are fast. For all x, if x is a racehorse, x has the attribute of being fast. That means if x is a racehorse, then it's fast, or all racehorses are fast. So these are various ways in which one can paraphrase in English the logical expression. All right, so let's look at existential quantification. There are really these just two primary kinds of quantification in traditional first-order logic or predicate calculus. Then exists or existential quantification is the other. So again, my syntax, we spell it out. If you are used to traditional textbook logic syntax, the symbol for exists looks like a backwards E. But in my case, we write it out, and so we have something that looks like this. There exists an x such that. And the key thing about existential quantifier, it says it commits you to there being one, at least one of these things, but there may be more, and you don't know. So it's uncommitted as to some of these details. So there exists at least one and maybe more X such that the following. So here is another example statement written out, and note how it's very similar in form to the previous formula, but the content, the meaning, is quite different. Here we're saying that there is at least one racehorse that is fast. And that's a very different statement from saying that if something is a racehorse, then it necessarily is fast. That's a statement about all racehorses, whereas this is just a statement that commits to a characteristic of one particular racehorse. It's also a way of talking about something without naming it. It's uncommitted in several important ways. And this is normal in human discourse. You know, I saw a dog at the corner, right? Is something you might say. You don't have to say, I saw the neighbor Smith's dog whose name is Fido at the corner. And just because I say that I saw one dog at the corner doesn't mean that there might not have been several others. Maybe this dog was particularly notable. It's something that parallels very well something we do very naturally in human natural language, human natural communication. So another way of looking at this is not only can you say it quite formally in a sort of artificial way, there exists at least one racehorse that is fast, but as with the universal quantifier, there's also a way you can, if you think about what that really means, that means there's at least one fast racehorse. That sounds considerably more natural in English. But if you recall the formal, stilted, artificial way of saying it, then you have a very easy literal reading that you can remember. So you can read this out for yourself, and it will still make sense. You'll still have a grammatical English phrase that you can recognize as being hopefully true, or maybe as saying something that you didn't intend and you need to work on it. Another thing we can do beyond existentials, where we don't name an individual, is in logic we can be definite and give an identifier to this thing that we're talking about. So let's say we want to talk about Secretariat the horse, this famous horse that won lots of races in history. We can say that there is an instance of a racehorse that we're going to call Secretariat the horse. Now remember, of course, this is just a programming language identifier, right? Calling it Secretariat the horse doesn't tell the system that it is a horse. It doesn't give it a name, Secretariat. It's just an identifier. And we could have said instance GenSim23 is a racehorse. A very important thing to remember is not to sort of anthropomorphize the software that you're writing. The machine really has no understanding of these arbitrary symbols. It's these logical relationships and logical formulas that give it meaning, right? So we can say that we have Secretariat the horse is a racehorse, and we can also say that it has the attribute of being fast. And that's in some ways rather similar to what we said with the existential quantifier, except instead of saying there exists some racehorse that is fast, at least one, we're committing here and saying, well, there's precisely one that we're talking about here. That isn't to say that there are others, but Secretariat the horse, at least, this one identifier, is a racehorse, and it does have the attribute of being fast. Okay, so we wind up with two simple logical paraphrases. Secretariat the horse is a racehorse, and Secretariat the horse is fast. So let's also look at some common errors now once we've got these basic building blocks. Say we want to formalize every parent has a child. We might go about formalizing it this way, and let me just quickly cross that out because it's not correct. Right? What this says is that if X is a parent, then everything in the world is a child of that parent, because we haven't really said much about Y. What we've really said is the following, also wrong, and maybe it's a little clearer when you restore the explicit universal quantifier. So you can read this as, if X is a parent, then for all Y, Y is a child of X. Well, we haven't constrained Y in any way, so that means everything is a child of this. If we have a parent, then everything is its child, including bookshelves and all sorts of other nonsense. Right? So we need to be a little bit more specific about this. And what we really want to say is what you see here. If we have a parent, then there exists one, and maybe more, y, such that y is a child of x. Right? Then we've constrained things a little bit. We haven't said anything in the world. We just said that if you're a parent, well, then naturally you can also say that you have a child. There is a child out there. And we could, of course, say many other things to tighten this up, that, of course, that child is a human, and that that child is related, and all sorts of other things. But this is at least a start for getting kind of the right general form out of this. And so understanding when to use the existential quantifier is really important. Generally, what you'd see is that it appears in the consequence of a rule. Right? We're saying if a lot of things are true, then there's some other thing in the world that has these following attributes or relationships to the stuff that we've talked about already in that rule. That's a very common form. And making sure that you don't read too much into the variables, and you understand that if I don't see anything else about y, then I'm saying it for everything in the world, and that'll generally wind up being kind of nonsense. Right? So I hope this was helpful in giving you some linguistic intuitions for getting started with certain syntax of mathematical logic. Of course, most of this applies to any other syntax, including your standard textbook formulations of mathematical logic. So if you like this, please click on like and subscribe, and tell me what you think. And there's lots of other resources, including all of the videos that I've already made about why you'd want to spend some time learning about logic, and some of the software that I've written for how to apply it. And lastly, if this all went by a little too quickly for you, I've put online a transcript, a document that has most of the content of this talk in it, as well as a second section where I'll be doing a separate video. And so you can look at this for this paraphrasing logic.pdf, and I'll also link that in the comments so it's a little easier to get to. All right, thanks very much, and hope you enjoyed this.